Okay, guys, can you hear me? Can you hear me? Hello. Okay, all right. Let's finish up. We are concluding this in the next. We are concluding this in the next 34 minutes. It is 26 past 1. So at exactly 2, we will wind up the lecture. So given what we've just discussed, guys, this is what we've concluded with. And we are saying that we can now look at some examples, and most of these we have actually preempted them. This is just more of a review of the properties we discussed. The first one being the linearity property. This one we did together. This one we have already covered. There is nothing interesting there. This is a change of scale. Nothing interesting. The second one is also change of scale. This is a change of scale. We've discussed all this. So nothing really interesting. We've heavily discussed such functions. Generally, you are having a happy moment now. There is nothing new. A brief table of the Laplace transforms. These ones we have preempted all of them. These are moments I also enjoy when I am teaching, because I can just flip over the pages. Yes, these ones are covered. Everything here is covered. Linearity rule, change of scale. This is more of a review. Laplace derivative, this one we have discussed today. The integral finished. Convolution, we have just finished the previous session. Now applications. Okay, the applications, these ones we have done all of them. All of these ones finished. Oh, here finished. Okay. Here, let me highlight something very briefly here. Here you must go back now to what we call partial fractions, guys. I think you remember partial fractions. When you're looking for a Laplace transform, you'll have sometimes to simplify the given function. You simplify it in such a way that what you've simplified is in line or is consistent with these very many definitions of Laplace transforms. Remember the table that we've just looked at up there. We've discussed quite many. Laplace of trigonometrical functions, Laplace of hyperbolic functions, Laplace of powers of t. Then we've looked at combinations. We've looked at theorems to do with Heaviside functions. So if you're given a function, please simplify it using any technique you are comfortable with. What you should know is the answer will always be the same. So simplify the function and use what is in line, or what definition of the Laplace function is directly associated with the simplified version of the function, and then you deduce the answer. So here we are saying inverse Laplace of quadratic or rational functions. And this is where partial fractions can come in. You can even bring in, by the way, longer division here, or the remainder theorem. And I insist you use any technique. There is also what we call the cover-up rule. you can use the cover-up rule if you want. Use any technique in simplifying or breaking down the function, breaking it down of that function, whatever it gives, so long as you break it down using known theorems, not creation of theorems that are only known to you in your small world of math. If they are known to everyone, then the answer you should get should be consistent with all of the other answers that other participants in that exercise of solving will get. I think I am very clear on that. Okay, with that said, because I don't want someone asking, what if I use this method? What if I am saying use any method you are comfortable with? At the end, you'll get the same answer. So here we are saying if you have quadratic rational functions, we have a function, a quadratic function such as this, we are saying the denominator could be simplified. If this is less than 0, complete squares. The good thing with some of these things, the completion of squares, this is something that is first taught in S2. If you went through a quality secondary school, here quality is relative. If you went through a quality secondary school, then in the S2, you did the completion of squares. So if this discriminant is less than 0, you can use the completion of squares. If it is equal to 0, you know these are perfect squares. And if it is greater than 0, you can go ahead and you look for factors. You use the factorization method. It is as simple. So me, I'm not going to be here and I start shouting completion of squares. You people are the teachers in some of those secondary schools. So since you're already teaching there, you go and revise what you were supposed to teach in school practice, and you remember these methods. So the first example is this one here. So if you look at this example here, you have s plus 3 over 4s squared plus 4s plus 1. If you look at this denominator here, just the denominator, you will realize that this denominator lies in the category of in category 1, where we have b squared minus 4s, that will be less than 0, and there you'll have to you can use the completion of squares, or you can use the completion of squares, and if you don't want to use the completion of squares, you can devise any other method that you deem necessary. I think this could be greater than 0. You can work out the discriminant. You know this is A, this is B, this is C. Then you substitute. B squared is 16 because this is 4. You have minus 4sc. The A is 4. So that is 16 minus 16. You have that is 0. You end up with those squares there. So this one gives you 0. This particular example. Where are we getting the 0? I have simply substituted in these ones. Just find b squared minus 4sc if you want to go along that. So this is A, the A is 4, the B is 4, the C is 1. 4 squared is 16. This is minus 4. Then A is 4, C is 1, is 16, 0, perfect square. That is why we are saying 1, if it is a perfect square, if you try to first of all simplify the denominator, since we have already known it is a perfect square, that is, if you divide the numerator and the denominator by 4, you end up with this. We have discovered it is a perfect square. Discovering that it is a perfect square, it gives you, where is my explanation? There you go. It gives you this term here. I need to change the color. Okay. So it gives you that term right there. Now, since this is the term you get, remember the whole of this now, since you have a half down here, in the next step, which I have highlighted in blue, this one here. So blue is derived from the red here. But remember, you remember what we discussed in terms of the definitions of the trigonometrical functions, the hyperbolic functions, the towers of t. Since we have s plus a half, then it is necessary that we express the numerator in terms of this square here. So we must express the numerator in terms of these halves. But remember, you already have s plus 3. This is s plus 3 over 4. If you look at the top part here, which is the numerator in red, you have s over 4 plus 3 over 4. S over 4 plus 3 over 4 is the same as s plus 3 over 4. But since this has s plus a half, given that I have to express this, remember we also looked at exponential functions, then it would be wiser to express this numerator in terms of these halves. And for me to do that, I just have to create or to come up with an identity. So this can simply be the same as s. I can say plus a half. This is minus a half. And this is a plus 3. This is an identity here. This is over 4. This thing here on the right-hand side is exactly the same as the statement, the fraction on the left-hand side. The only difference is I have a half minus a half. Definitely this cancels out and I remain with the s plus 3. So in doing so, I have come up with what I am interested in. So from this, I can have now my s plus a half. Then I can take this one alone. And this is my 3 minus a half. But remember, the whole thing is over 4. So the whole thing being over 4 is the same as having this over 4 because the denominator is the same. This is exactly what we have here. There is no big deal here. And in having this, once you simplify this one here, simplifying that, it will give you this 5 over 8. So once it gives you 5 over 8, simplifying this one gives you 5 over 8. So you get the 5 over 8, the whole of this one here. This one gives you 5 over 8. But remember, there is this s plus a half squared. So that's why you get the 5 over 8 into this one here. Then remember now you have s plus a half over 4, but there is over s plus a half squared. This cancels with the square there. That's why you remain with 1 over 4, this 4 here, which is that 1 over 4. And then it is s over s plus a half. Yes. Wait, so I think you are following. Sorry about that small stop. Okay. So in getting this, how do you go about this guy? So when you get this now, you can just come down here and you simplify the thing without any problem. Once you have this and you have that, then you go and you look for the Laplace from the definitions that we looked at. Then you realize that this one here is the same as e to the minus a half t, and then the 1 over s plus a half squared this is the same as t e to the minus half t. And that is the answer. There are no questions there. Everything is very obvious. But I'm going to request, given that time is moving fast, I want to first go and I solve ODEs using this Laplace transform, because all of these other things here we have done. Here you can use partial fractions. You remember how partial fractions work. You look for ABC. So let me first solve the ODEs using this Laplace transform. And once we do that, if we have some time, we can come and look at these obvious examples. These ones you can go and do all of them. So my interest now in the remaining minutes is solving an ordinary differential equation. Here I want to use the definition of the Laplace transform of a derivative, which we discussed. We started with that today, guys. Right, so let's look at a very simple example here. So in this very simple example, we have solved the differential equation. The differential equation is this one here. It is an initial value problem. So you have, this is a second order of degree 1. And it is non-homogeneous. I think you still remember your D is 1, guys. So since it is non-homogeneous, we have these initial conditions. Now remember, we looked at the derivations of the Laplace transform of a derivative. They are already summarized in this table here. So in this, we can now compute. We want to use the Laplace transform to solve this equation. If you use the Laplace transform, for starters, if you take the Laplace of the entire equation here, that is this first step. You have L of y prime prime minus L of 5y prime plus L of 4y, which is the L over that one there. Now, the Laplace of e to the 2t is 1 over s minus 2. You can compute this one and you get that one. Then what about these ones here? These ones, they are also very direct. This is where we are going to now substitute. Now we are going to deal with the substitution of this. Remember, we apply all the rules. Here you can take the 5 out so that it is 5L. I know someone was complaining whether it is a box bracket. Please, it is a curly bracket, but I struggle to write. This is 5, guys. This is minus 5. This is plus 4. You have a 4. You take it out. This is a Laplace. This should be a curly bracket, but I struggle to write that one. This is, you can now factor out. You can take the 4 and the 5 out. Once you take those ones out, now remember, we have already discussed the Laplace of the second derivative is the whole of this thing here in terms of y. The other one, we derived it in terms of f. So where there is f, simply substitute y, which is this one here. Then, if we have the Laplace over the second derivative, so what you have as this second derivative here, guys, just the blue here. Maybe I need to check this out again by, I'll simply do it. This whole blue here is this term here because it is the second derivative. So blue goes with blue. That is the expansion. Now remember, I told you you can take the 5 out and you have minus 5 Laplace of y prime. But we already know what Laplace of y prime is. So the Laplace minus 5 Laplace of y prime. This is a curly bracket. So the Laplace of the one in red, hopefully we are together. This is the Laplace of the derivative. This one is the whole of the red here. I'm hoping we are really together, guys. So red goes with the red. Here there is nothing to worry about. Now it is 4 L of y. Now we compute. We substitute now. Remember, when we say the L of ft, this is the notation we have been using, guys. L of ft, this is the same as fs, because by definition of Laplace, you have E minus st f of t. Okay, so it means that now, since we have the Laplace of y, instead of L, which is y of t, this one can simply be written as capital Y S. Hopefully we are together there. There is again nothing big in that. Okay, so instead of Ly, we have now substituted with ys. S of y0, this one remains s of y0, because here we are going to impose the initial conditions. There is no L here, so this comes back, that comes back. Now here we have minus 5 s, Laplace of y is ys, minus y0, which is that. This is plus 4 Ly is ys. What do we do here? We can now simplify this in terms of, the ys. Guys, just simplify this in terms of ys. If you look at this one, if we try to do that in terms of ys, the first one with ys is this term here. So what does that mean? That means that you have s squared. The second term with ys, you have s 5s ly. That is this term here. I think we are together. So this is the minus 5s. This is minus 5. Then you have s because of this term here. Then lastly, you have 4ys, this term here. You have this term, you have that term, and that term. So this is why we have plus 4 here without the s. So you take this one in brackets, and this whole thing has a ys outside. I hope we are together. So you need to correct this. You have a 4, so what you are having here, we need to correct the brackets here. The brackets are not properly written. This box bracket should end here. That is a box bracket. And what you see as a box here should be a parenthesis. This should curve like this. And this one curves like this. I hope I am clear there. So once you take out the ys, what do you remain with? You remain with, now guys, please pay attention, pay attention. So what we have now here, remember we have y prime of 0 is 0. Since y prime of 0 is 0, this one goes to 0. That whole thing disappears. Y prime of 0 is 0. Then we have y0 is 1. So if y0 is 1, it means here, this is simply s, because this one now becomes 1. Also this one here becomes a 1. So since this is a 1, we have minus 5 times a minus 1. This becomes a positive 5. Hopefully you are following. By the way, can you hear me? Can you say a yes in the chat, and I get to know that you are following? Can I hear a yes if you can hear me? Okay, good. Okay, so we have a minus 5, but remember when you throw in the conditions, if you initialize with these conditions, y0 is 1 and y prime 0 is 1. This is at t0, y is 0. So y0 is 1. We throw the 1 there, but you have a minus 5 with a minus 1, which is a 5. That gives you a 5. That gives you a positive 5. Then in here, remember this is 0, but you have minus s. So you have a minus s that comes here. That is the minus s. That is 5 minus s. This term here is the term you see here. So after doing this, what do you have to do? The only thing you have to do now here is you make ys the subject. How do you make ys the subject? Since this is what you have, this one has ys, but this term doesn't have ys. So it means you have to take this term here on the other side. So we cross this one out and we take it this way. It is positive. This will be minus, this is 5 minus s. This is a 5, guys. This is 5 minus s. It's not coming out clearly. So you have digit 5 minus s, which we have taken on this side. We have removed it from there. If you simplify the term in blue, simplification of this term in blue, if you simplify this term here, I hope we are together. That is 1 over s minus 2. This term here does not have ys, so we've taken it to the right-hand side. That is the minus 5 minus s. It will give you this whole thing here. Okay? It gives you this one here. So since it gives you this, you now make ys the subject. To make ys the subject, it means you'll divide by this term on both sides. You are going to divide by this on both sides. But before you even go into that, if you use the factor method, you will realize that if you use the factor method, guys, you are going to realize that this term I have underlined here, or the one I have circled, if you look for the factors of this is going to give you s minus 1, s minus 4. This one here is the same as s minus 1, and at the same time, this is a product of s minus 1, s minus 4. So since it is s minus 1, s minus 4, I make ys the subject. What will this give me? My ys will be the whole of this term here, this one. It will be that term, which is s squared minus 7s plus 11. That's the numerator. Over s minus 2, which s minus 2 is this one here. Then I have to divide by this one. Remember, this one was on the left. I divide and it comes to the right. So the s squared minus 5s plus 4 is the s minus 1, s minus 4. I think we are clear there. That is what you get in that one there. Okay? So with that said, we can now hit the last nail. in here, hitting the last nail would imply that we have this. You remember partial fractions. With the partial fractions, if you have this is the same as, because all of these are different terms in the denominator. This is your partial fractions. Go back to A-level work, and you can go back to the different techniques of integration. You still looked at partial fractions. This is the A over S minus 2, B over that, C over that. What happens is you look for A, you look for B, you look for C. I'm sure you still remember how to do that. Just look for A, look for B, look for C. Just in case you have forgotten, there are examples where I have demonstrated that up this way. There are a number of examples. There is this example here where you look for A, B, and C. We are going to go through all of these examples. I think I had another one around here. Yes, there is this one here. You see this term here is expressed in terms of partial fractions, because when you look at this is S cubed. We pulled out S. You remain with that. So long as the factor does not exist, you have BS plus C. Then you look for the A, B, and C. So this one will show you. This is already a work that is obvious. But for those crammers who crammed in A level and they think they are going to survive on cramming, go back and revise your A level. And you remember what you crammed that has already disappeared. I told you cramming is a curse which makes you suffer in the entire life of your academia. If you choose not to cram, academia becomes lighter. All right. So please you go and here you only have to look for A, B, and C. If you look for A, B, and C, it will give you A is minus a half, B is 5 over 3, C is minus 1 over 6. And once you have this, you just factor these out. You have minus 1 over 2, but we all know that 1 over S minus 2 is the same as E to the 2t. We already even have it here. This E to the 2t, this one, we got it as 1 over S minus 2. Okay? Then you go to the next one. This is 5 over 3. Take the 5 over 3. This will be 5 over 3 E to the t. And then the last one, it is 1 over 6. This is a minus 4. This is E to the, this is minus 1 over 6 E to the 40. So if you solve that ODE, if you solve that ODE using the Laplace transform, you get the solution as this answer here. That is what you get, guys. This is what you will come up with. Okay. So once you get that, the rest becomes obvious. Is that okay? The rest becomes obvious. So there is really nothing much in this whole thing here. The rest here, guys, you can just go through these other examples. There is another example here. This is the powers of t. You know it is 2 over s cubed, which is there. Now you bring back our definition of the Laplace transform of a derivative. You substitute for this one, substitute for that one. These are the substitutions here. Then you apply these conditions. Where there is y prime 0, you throw there a 1. So this one here will become a 1. You can even substitute them straight away. Y prime 0, this is 1. Then y0 is 0. This whole thing here is 0. You substitute. This will simply be your s squared. This y is now the s, that is minus 4s, which is this one here. There is a 4, then ys. Then what you see as s, this was 2 over s cubed, this was 2 over s cubed. But remember, there is a term we have picked from here without s. What is that term? The term we've taken there is this one here. Remember, y0 is 0. So since y0 is 0, the whole of this here is 0. But we have a minus 1 here. So we have a minus 1 here. Since we have a minus 1, this is minus 1. And then what about this one? This is 0. Because y0 is 0. So y0 being 0, minus 4, that is 0. So we have minus 1. There is minus 1 on the left. If you take it to the right, this becomes what? This becomes plus 1. And I am sure if you simplify that, the LCM is s cubed. If you divide this by this, you get 1. This is 2, which is that 2, plus this one divided by 1, you get s cubed plus 1, which is s cubed. So this term you see here is this term you see here. I think we are clear there. So this one is modified by the extra term that is this way, that you will take on the left-hand side. That's why this one becomes that. And once you get that, the rest is just petty algebra of simplification. And if you go through that, this is where you end up with as if this number is incomplete. Because this is another, okay, you can finish it. Once you get this here, you can use, here you are in for a treat, because you have, from this, let me conclude with this, guys. Sorry, I know it is already 2. I'm finishing with this. For partial fractions, I think you know what you are going to do here. This one, you are going to have 1 over, actually you're going to have a over s plus b. This one will be plus b over s squared. This is s squared plus c. This is over s cubed, because you have, this is s to the power 3. But remember now, this is a square. Now you remember when you have a square, I think, do we have a problem?